Now, to get the webinar started, here is Ryan Ritz from Paratherm Heat Transfer Fluids. Ryan?
Thank you, Molly. Thermal fluid technology has evolved over many years, and the advantages of fluid heating and cooling are well established. Yet there are still common spheres of confusion that need to be addressed. The preliminary step in any thermal fluid operation is also a predominant source of such misunderstanding. That's how to navigate through the vast array of available fluid options and select the product that best fulfills your specific operating needs. With a host of different manufacturers, suppliers, and distributors, each offering a list of product offerings, it can become difficult to know where to start, let alone how to optimize the selection process. So to get started, we're going to talk about charting the course of introducing the 7 thermal fluid Cs. First, we're going to discuss different classifications of thermal fluids. The very top-down, looking at the ways we can break this, all these technologies down. And then we're going to get a little further into that and talk about the capabilities of each type of classification. From there in the selection process, you need to consider the specific conditions for your system and operation, what you're looking to fulfill and which technology is best suited to do that. From there, the next consideration would be to find something that's compatible with all the equipment that you're going to be introducing the fluid to and any other fluid that might have already been introduced into that system. From that point, we've already really discussed the basic overall generalities, and we probably have our technology in mind. So we'll move on to the cost factors versus performance considerations for any thermal fluid type system. There's definitely ways that you can maximize the cost, but is it something that's going to be an over-design for your system? We'll look at what to look for in those circumstances. From there, when we've narrowed down to perhaps 2 or 3 very similar fluids, it's going to be what the most important steps of competitive benchmarking will be for you in your operation. So what data to look at side by side between 2 different products or 2 different suppliers. And that being said, the characteristics and credibility of the actual suppliers you're looking at should be a key point to look at when you're determining the overall value of your selection. So credibility of product claims and the supplier credentials are going to be the final step that we look at to narrow down your final selection for thermal fluid. So just to go through quickly the navigation of how we're going to present this material, and it's going to really follow along what your selection process will likely be in real-life operation. So we're just going to define the scope of the presentation to begin, introduce a reminder of what we're talking about when we say thermal fluids or heat transfer fluids. From there, we're going to move more in depth on the selection process, focusing on the fluid aspects, and that's, again, the classification of thermal fluids and capabilities. Moving next into the system focus of your selection, and that's talking about the conditions of your system and the compatibility. And then moving our way through the end of the 7 Cs in our navigation, we'll talk about how to narrow those selections with cost considerations, competitive benchmarking, and then verifying the credibility of your supplier and any product claims. So to begin with the scope, heat transfer fluids. Heat transfer fluids are also known as thermal fluids or thermal oils. They can be referred to as heating or cooling fluids, and oftentimes in certain industries just referred to simply as hot oils. For our purposes here, we could use any of those terms interchangeably. You may see us going back and forth between the 2 most common terms, which are thermal fluid and heat transfer fluid today. Keep in mind that we're referring to the same technologies and same subject matter when we interchange those terms. Now, the key point behind heat transfer fluid technology is the ability to generate high temperature, the ability to generate high temperatures at low system pressures. Now, heat transfer fluid technology offers safety, low maintenance, and extended operating lifetimes when compared to traditional technologies such as steam heating or direct fire heating. This technology offers highly efficient, non-corrosive heating and cooling and allows for accurate temperature regulation and uniformity across the entire system. So for the purposes of this webinar today, we're going to be looking mostly at high temperature thermal fluid heating. Now, a lot of these criteria can also apply to low temperatures, but for the general purposes, we're going to be focusing on high temps. We're also going to be looking mostly at non-aqueous fluids, so we will present some aqueous technologies, but we're going to be talking mostly about non-aqueous. From there, we're going to be looking at narrowing that further into natural and synthetic organic hydrocarbon-based fluids. And for system purposes, we're looking only at closed-loop circulation, so we're not talking about anything really open bath, though some of the properties will apply as well. So moving forward, we really want to narrow this down and talk about why proper fluid selection is so critical. Using the proper fluid is paramount to your operation. And selecting the wrong fluid, you're likely going to lead to accelerated degradation, equipment failures that are associated with those degradation products, fouling of the fluid onto surface elements in the equipment, increased maintenance activities, and decreased efficiency on both the heat transfer and total system operation. And keep in mind here, when run properly with the correct fluid, this technology for heat transfer systems are safe and low maintenance by design. The inherent dangers of any high temperature operation will definitely increase exponentially if these factors are taken for granted. So this is why fluid selection is so important. If you're selecting the proper fluid for your operation, you're going to be optimizing operating specifications. You're going to be looking at optimizing this design of equipment, this huge capital expense that you had. By choosing the wrong fluid, you're going to be really limiting what that equipment design is capable of doing. So by choosing the proper fluid, you're going to be able to choose something that's going to extend the operating lifetimes. You also need to look to optimize your budget. And you know that there are limitations when selecting something like this, and we need to make sure that the budget is also kept in mind. Superior fluids, what are we talking about in that? So when we finally choose this proper fluid, what does that mean? What are the boxes we're going to check? It's going to be a highly purified product. It's going to offer you high heat transfer efficiency, and it's going to offer you superior thermal stability compared to alternate options. And one thing that's often overlooked at the end of this, at the end of the day, is the partnership that you should have with the supplier of that thermal fluid. So let's move into actually going through these thermal fluid Cs. And starting off with the first of the 7 would be the high-level look at fluid technology, where we're talking about classification of most commonly transferred fluids. So starting off at the bottom of this scale, you're looking at 3 different general classifications. You have aqueous-based fluids that use water as the heat transfer medium. Now, keep in mind that water is the most efficient and most the highest quality, best product that you can get for heat transfer in general by theory. Okay. So the problem with water is it freezes and it boils. So you have a very limited range where you can actually use water for your heat transfer fluid. So to extend that out, different additives like glycols or salt-based solutions or brines can be added to an aqueous to water to make an aqueous-based heat transfer fluid. But you're still really limited to that point, and there's pros and cons behind using those types of fluids. So moving from there, we move up the temperature scale, and this is really where we're going to get into our focus because these are the most common hot oil thermal fluids. You're going to have something that could be based on a type or general classification as a mineral oil, and from the temperature scale going up, you can either have a Group 1 type base fluid for that. And moving up from there, what would be more ideal in this group would be either Group 2 or Group 2 plus beyond that in the mineral oil area. And then moving to the top of the capability list for classification, temperature capabilities, you get into silicone-based fluids and aromatic blends. Also keep in mind, for simplification of a graphic on this, we don't go to 2 different areas, but aromatic and silicone blends also bring you back down to the bottom of the scale and allow for extreme low temperature cooling as well. But as we said in the scope of the presentation, we're focusing on high temperature heating here. So now, getting into the area of the hydrocarbon-based heat transfer fluids, the non-aqueous heat transfer fluids. That breaks into two categories. We have the natural organic hydrocarbons, and this is base chemistry that consists of a selected mixture of molecules generated during the crude oil process, refining process. So that's why we say natural organic hydrocarbons here. So mineral oils are featured for their non-toxic, efficient, and cost-effective performance. And this is a key point here when we're talking about selection process. Budget-minded and also capability-minded, they're very good at a range from moderate to high temperatures. So you're looking at a max operating temperature between 550 to 600 degrees Fahrenheit. So from there, you can see where we're already starting to, by classification, limit our selection process. One key point behind the natural organics, often referred to generically as mineral oil-based products, the quality and purification levels are very critical here. Okay, so color is going to be important. If you have coloration to these natural organic mineral oils, that's often going to mean that there's either a high level of impurities or a high treat rate of some kind of additives that are in there. And those are all considered impurities that will foul your equipment before the actual base chemistry breaks down. So you're looking at highly refined, specialty engineered options are well worth the added cost due to their higher stability and performance levels. So right off the bat, when we're talking about classification of the fluids in your selection process, I would urge you to only look at something that's going to have an engineered quality to it and a very high purification level. And I think along the lines of your selection process, that should become inherently obvious when you're looking at what kinds of fluids you're looking at. So you're going to want to likely dismiss anything that has a coloration to it as a general rule of thumb. Now, moving into the synthetic organic hydrocarbons, also referred to more commonly as aromatic-based fluids. These are where a base chemistry will be produced from specifically formulated chemical synthesis. So you have a target that you're trying to synthesize through a chemical process, and it can meet certain criteria or performance levels that you're looking for. So aromatics are typically going to be benzene-based. They display a very high thermal stability at higher temperatures, and then also offer lower startup temperatures, more so than the natural mineral oils will. You'll achieve operating temperature maximums above 650 degrees Fahrenheit. But that benzene-based ring structure is really the key behind this chemistry here. The double bonding yields superior stability. It's able to handle the heat energy much better, so it allows you to get to higher temperatures and get longer lifetime of the fluid. So the trade-off considerations with that, in a perfect world, you would be able to love to have something that's the most stable, that gives you the best range of temperatures. But the issue here is going to be you have to trade that off with cost considerations. You also have to consider an environmental situation with the aromatic-based fluids. As you can tell, if they're benzene-derived, there is the consideration that you need to put in with the environmental issues, disposal issues, some process limitations that you have. All that needs to be taken into account when talking about the classifications. Okay, so moving on from there, we looked at classifying these fluids and breaking them down from the highest level. In just a quick review, we have the aqueous-based fluids. If you're anywhere outside of the temperature range of water, or what the temperature base can give you in terms of capability, you're going to experience the issues of boiling, freezing, or outside of the performance areas. So when we look at capability as part of the navigation through your selection process, you really need to take into mind that you have an operating temperature range specific to your operation, and you need to choose fluids that are going to be capable of handling that. So the fundamental product capability that you'll have to look at right off the top of things would be, what's your operating temperature range? And understand that, unfortunately, there's no universal way that suppliers will define these minimums and maximums. Sometimes you'll see minimum pumpability being defined as the minimum temperature, minimum startup sometimes. what you really should look for when considering an operating temperature range is your minimum operating temperature. What are you actually going to need functionally from this fluid to transfer heat at your minimum possible operating temperature? Because that's going to be the performance characteristic that's going to be most relevant to what you're doing. The minimum operating temperature, and what I would recommend would be finding something where you have efficient heat transfer and turbulent flow, where the fluid is still maintaining that at a certain viscosity and density rate. Okay, so moving up from there, the maximum operating temperature is really paramount to the lifetime of the fluid, and it will limit quite a few options when you're looking at the selection process. So the first question you likely should get after all of the pleasantries on the phone with whoever you're trying to buy your fluid from would be, what's your maximum operating temperature? What are you looking to get out of this product? And that will be defined as the temperature at which the particular fluid you're looking at will be able to give you efficient performance and will be able to last a reasonable amount of time in your system if you operate it correctly. Okay, so maximum operating temperature, if your product, if your procedure is calling for you to run the fluid at 600 degrees Fahrenheit, and you're looking at a fluid that's only rated up to 450 degrees Fahrenheit, obviously that's not going to be an option for you. Now, where it gets really tricky is where you have an operation calling for 590 degrees, and the fluids that you're considering are only rated to 600 degrees. So that's where the selection process gets a little bit more complex, and you have to start paying a little bit more attention to what's going on with the fluid options that you have. So minimum startup temperature, key point here. There's times where we get calls and it says, I'm operating in a region that features cold weather. Over a long period of time, we have temperatures that get down into negative 30, negative 40 degrees. And if the system goes down, if we need to perform maintenance, we need to be able to start that fluid back up at that temperature and make it pumpable. And the issue is going to be they also need to run the fluid up to 550 degrees Fahrenheit. So your options become extremely limited at that point to what kind of technology you can have that has that wide of a temperature range available to you. So your climate and environment are also very important capabilities to consider when you're looking at the heat transfer fluid capability. Fluid with a minimum startup temperature above your environmental ambient temperature is going to cause problems when you have to have maintenance time, when you have to load the fluid, or if you have an unexpected system failure, unexpected shutdown. You need to make sure your fluid can actually be pumped through the system to start up. Now, that's important from a physical standpoint, that you need to get the fluid moving. What also becomes extremely important is there's a lot of thermal stress that happens during startup of a fluid. There's high heat being applied to a fluid that's not at its optimum viscosity to move through the pipes. So a fluid with a lower startup is going to offer you much better fluid longevity and protection against premature degradation during startup process. So some other fundamental considerations that you need to have behind the products you're looking at. Level of impurities. We talked about why quality and lack of impurities of a mineral oil heat transfer fluid are so important. So you need to make sure you're looking at the fouling aspects of the impurities that you have. If you have a fluid that's going to start off with a darker color, has a lot of higher impurities in it, group 1 type based fluid, that's going to cause fouling problems at higher temperatures. So that's a fundamental product capability. Another product capability inherent to the product you're looking at is the presence of an additive package. So additive packages sound nice. They often get applied as some extra protection against some kind of a degradation mechanism that you're looking to avoid. But be really careful based on those claims, because typically what happens when you have a higher treat rate of additive packages that are being advertised and touted, they're going to typically narrow the operating range and the capability and eventually the lifespan of the fluid you're looking at. So you want to make sure that if you're considering fluids that advertise a high additive package, for whatever reason that might be, take an extra step in looking into the purpose behind that. And if it's something that you truly need, or it's something that you can push back on and say, you know what, that doesn't sound like it's really contributing to what my ultimate goal is, so we don't really need to consider that. And then again, there's just sometimes a consideration of preference to synthetic versus mineral oil products. Try to avoid those preferences and look at the actual capabilities versus cost performance. And we'll get into that later when we talk about cost. So temperature claim capabilities. So if you know nothing else about the operating conditions of your process prior to the selection process, at the very least, you should know the required operating temperatures. That should be well established. So while there's certainly overlapping ranges, each of the three basic heat transfer fluid classifications have associated temperature limitations that serve as the primary criteria for your fluid contention process. Looking at this, you see the limitations of the glycol-based products, aqueous-based products in comparison. So, you have low-grade group 1 based fluids compared to the ethylene glycol compared to the low-temp aromatics. And you could see really here the limits of the glycol-based products are around 350 to 400 degrees Fahrenheit. And at that point, what you're doing is you're really getting to the limitations of pushing some risk when you get to those temps. So, again, sticking with the scope and looking right at these natural hydrocarbons versus synthetic hydrocarbons, the non-aqueous options, we're going to, eliminate those aqueous-based ones and define the limitations based off of these criteria. So low-grade group 1, again, we should have already, if you're following the best practices recommendations of this webinar, and most likely most thermal fluid professionals, you would already eliminate the option of a group 1 based fluid simply because it's not going to offer you any performance benefits. It's not going to offer you anything that's going to be truly an advantage other than cost. And at that point, you're sacrificing a lot of performance and a lot of fluid capability for a cost factor. That's really, when you compare, not too much lower. So looking at this hydro-treated natural hydrocarbon, group 2 base oil chemistries and above, that'll get you somewhere around 575 degrees Fahrenheit capability. Now, looking into specialty engineered formulations from heat transfer specialty companies, you're going to get upwards of around 600 degrees Fahrenheit as your maximum temperature capability. Now, keep in mind, key point, comparing fluids against each other, and we'll get into this when we talk about benchmarking and credibility of claims. But temperature maximums are splitting hairs when you go between 600 Fahrenheit and 610 Fahrenheit. Anything within that 10 to 15 degree range, you should consider all things equal at that point and really look to the supplier to define why they define their maximum operating temperature as such and give you data to prove why one might be better than the other. So right off the bat, we have between natural hydrocarbons, mineral oils, and synthetic hydrocarbons or aromatics, you've got a clear-cut line of what you can choose from here. You've got anything above 600 degrees Fahrenheit or approaching right around that limit, you're going to need to start considering something in the synthetic hydrocarbon range. High-temp aromatics give you capability well above 650 in some areas, but that range between 600 and 650 is a popular temperature range. So that's where you need to start considering these aromatic-based fluids. They're also a non-aromatic classification of synthetic hydrocarbons that will give you some mid-range temperature capabilities. So those are a specialized area that we'll look at as well. So for performance capabilities, so we just talked about temperature capabilities, now let's get into performance capabilities. So what you need to look at for the capability of the fluid as a primary factor is functionality based off of 3 key features. You want to ask about the thermal stability of the products. You want to look at the heat transfer efficiency of the product. And as we keep harping on here, but it's very important, the product purity. So those 3 areas are going to be the primary considerations of capability for performance. How stable is the fluid? If your selection or your options for thermal fluid supplier can't answer these 3 primary, give you information and data or give you an opinion based on these 3 primary capabilities, probably someone you want to consider putting at the bottom of your list for options. Anyone that's specialized in this area should be able to give you data or give you some kind of criteria based around these capabilities on why their product is better than something else you're considering. So thermal stability, and we'll talk about each one of these as we move forward in a little bit more detail, but thermal stability, efficiency, and purity are three key capabilities you need to look at. Some other areas where you can consider, if all those things are equal, looking at the expansion rate of the fluid, and that's going to tie into the system sizing. One that's a real headache for a lot of professionals in the thermal fluid range is flash and fire points. I just want to make a kind of a public service announcement here. Majority of thermal fluid systems are going to run well above the flash or fire point of the selected fluid. I would consider flash and fire points mostly for storage and shipping capability of the fluid and not so much for the actual operating limitations. If there's any questions based off of that, try to catch us during the question and answer session on why that's the case. But I would not use flash and fire point as a primary consideration for choosing one fluid versus another. You can get yourself into some real headaches and complexities there by doing that. Another area to look at is oxidation resistance, and we talked about additive packages. There's some inherent oxidation resistance with different chemistries. There's also the ability to introduce additives, antioxidant additives to help out with that as well. So if you have a system that's inherently going to produce problems with oxidation, you should look at ways that you can improve the operation and the system itself to avoid that. But if you determine through that process that it's somewhat unavoidable, seek out a product that has some oxidation resistance capability. Startup temperature, and we discussed that before. That's a secondary feature to look at in capability. The vapor pressure. And then what we're going to look at as one of the major C's here later on is the cost versus the performance. What am I paying for, and am I getting enough advantage to justify what I'm paying for that product? Or do I need all of those advantages? Am I overpaying for a product that gives me more than I actually need? And we'll talk about how we determine those two different things. So we talked about classifications, and now we're going to move into the, we talked about capabilities, and now what we're going to do is we're going to move to the next area, which is the conditions of the fluid that you're looking at. And this is moving out of the realm of the inherent fluid focus, and now we're moving into the realm of the conditions of your system and how they dictate your fluid selection process. So, looking at the process specifications that you're considering. Now, this is something that you really can't change too much or can't tweak. This is the area where your system is located. This is the equipment you've already selected. This is the application and the process that your plant is producing. All of those have inherent limitations that help you choose one way or another on fluids that you're going to specify. First and foremost, we look at, is it a food grade application? And beyond that, let's go a little broader. Does it require food grade rating? It may not be food production per se, but maybe you're looking at packaging or pharmaceuticals or some kind of medical devices that require a safer product to be used, and there's limitations based off of that. Well, that makes your selection process quite simple at the very high level. If it's that kind of an application, you need to make sure you choose a fluid that has NSF HT1 incidental food contact rating. There's a slight but obvious and key difference between the more common H1 designation for lubricant oils and the HT1, which is specific to heat transfer fluids. And that's an important designation that you should not confuse. We've seen some folks that are using a fluid with an H1 designation, and what you should be concerned off of that is maybe someone sold you a lubricating oil instead of a heat transfer fluid for your system, and there's a key difference between that. Now, a food grade application typically, depending on what you're producing, are going to require temperature capabilities above 500 degrees Fahrenheit. So right there, you're giving yourself two key criteria to base off of your system conditions that are going to really limit your search. you're likely going to have something in that HT1 incidental food contact. Your aromatic-based fluids are not going to meet that kind of rating. So you're limiting yourself there to the natural organics or mineral oils right from the beginning. And then you're going to want something with a capability above 500 Fahrenheit. So with some cushion room there for your capability so you don't go above. Is this a continuous process? That's the next condition that you should look at. In a continuous process, there's going to be long-term exposure to higher temperatures. There's going to be perhaps an accelerated breakdown. And what you're going to really need to do with a continuous process is make sure you have a fluid monitoring system or a great relationship with your supplier to monitor the fluid so that you don't have unexpected failure, degradation, or maintenance practices that come up because of that. So in a continuous process, you're going to want to limit your selection to something that is designed for that and can stand up to the long temperatures over a long time. So that's something key to ask your potential thermal fluid supplier, is this fluid better than the next for a continuous process? You're going to want to consider the conditions of your local climate. Cold weather areas will need something with a lower startup capability. So you're getting down to those secondary considerations, but that's a condition that you can't change unless you move where your business is operating. So take that local climate and that cold weather area into consideration. Is your system that you have existing open to atmosphere? If it is, then you're going to have oxidation issues. Also, under those circumstances, you're going to have irritating vapor odors, perhaps, depending on the fluid selection. So you're going to want to limit your choices based on those things as well. You want something with a little bit, ask the suppliers, it's going to create a vapor, what kind of vapor odor is going to be created based on this, because you've got people in your plant that you want to make sure have a workable environment to be in. So as we said in the scope, we're limiting this to closed-loop systems. But that being said, there are certain system designs that feature more of an open atmosphere than others. So that's something to consider. Is there a heat-cool cycle necessary? Just because a fluid is capable of operating between your entire cycle doesn't mean that it's designed to quickly go from heat to cool. So you're going to want to look for something that's considered either a heat-cool fluid or discuss that with the supplier to make sure just because the fluid range covers your entire cycle, the fluid that you choose based off of that may not have the inherent capabilities to transition quickly, and you're going to be cycling much slower. That's a lot of downtime and could possibly really hurt your application if you're not using a heat-cool fluid that's capable of that cycle. And is this an existing system that's already been in operation? This perhaps might be the most important condition that's going to dictate what you're doing. An existing system will have existing fluid in it. You're changing that fluid for a reason. Maybe it didn't meet your capabilities. Maybe it broke down. There's a lot of degradation. There's some fouling that was happening in the system. Under those circumstances, you're going to have compatibility issues with the degradation problems that are left over, products, carbon sludge, carbon buildup. But you also want to make sure that whatever existing fluid was in there is compatible with the new fluid that you're choosing to put in. So two considerations and two selection processes from that point. One, should I be choosing a fluid that has the same chemistry, same compatibility as the fluid that was in there previously? Or if you're not going to be doing that and you're choosing to go to a different fluid for whatever reason, you need to make sure that you're taking the proper cleaning steps to get that fluid out of the system so it doesn't contaminate the new fluid. So those are conditions that we're looking at based on the thermal fluid systems that are inherent to what your operation is. And we just talked about compatibility and why that's so important, right? So at this point, we're going to look at compatibility concerns, okay? And compatibility concerns can come in the form of a few different areas, one being the materials of construction in your system. So one of the key conditions of your inherent system is, I have a system here, it's got certain polymers, it's got gaskets, it's made from certain kinds of metals. I need to make sure that I'm choosing a fluid that's going to be fully compatible with all of my equipment. That comes in the form of pump seals, that comes in the form of the heat exchangers that you have, everything along the way, you want to make sure that you're looking at materials of construction that are going to be compatible with the fluid that you choose. Key point here with aqueous fluids, you want to make sure that there's no dissimilar metals that come in contact. The galvanization process, when you're looking at aqueous fluids, that's a serious concern for causing corrosion in those kind of systems. But even more, one area that you really need to look at with the non-aqueous fluids, the polymers, seals, gaskets, etc., need to be rated, 1, for the temperature that you're looking at, and 2, for the fluid that you're putting into that system. So that's something where you need to really get together with the equipment manufacturer and the fluid suppliers that you're choosing, and everyone needs to be on the same page with that. Fluid suppliers should be able to provide you with a fluid compatibility or polymer compatibility chart. The majority of metals out there are going to be compatible with hydrocarbon-based non-aqueous fluids. One thing you need to be concerned about is copper is usually a tricky one. If it's on a heated surface, there's the heat sources behind that copper on the other side of the fluid. That can be a catalyst for oxidation. So whenever copper is present in your system, make sure that you take the extra step of considering that compatibility with the fluid. Talk to the suppliers that you're looking at. Even more common, though, and more of a cause for concern for compatibility is the fluid-fluid compatibility. So existing fluid replacement, extremely important. Get it tested. Make sure that whatever the degradation level is in that system isn't going to be something that's going to immediately contaminate and hurt the new fluid that you're putting in. When you're looking at existing fluid replacement, top off versus drain and recharge is very important. When you're topping off a fluid and you have a aromatic type base fluid, or you have a fluid that's in there of a certain kind of classification or chemistry, and you decide to switch suppliers and either go for a fluid that has A, more capability to give you an extended range, or B, something that might be more cost effective for you, odds are you're going to run into problems with compatibility of the fluid that you're putting in or the fluid that used to be there. So a top-off issue is very important to consider that, because you're putting a smaller percentage into a bulk of a fluid. But it's also really important, even though you drained the entire system out, to make sure that what you have left in the system is going to be at a percentage that's not going to cause problems. And rule of thumb that we typically see is around 15% of the fluid, just due to the inherent nature of most systems, will be left in that system at the low points. It's virtually impossible to drain, just a straight drain, gravity drain that system and get all the fluid left over. So having that conversation of what the previous fluid was and the procedure in which you're removing that fluid, having that conversation with your potential supplier is going to be key in determining compatibility with the new fluid you're putting in. And what are the issues with that? Well, miscibility is one key issue. If the two fluids are not able to fully mix together, you're going to have phase separation. Phase separation can cause all kinds of problems with vaporization of one fluid over the other, pump cavitations, unnecessary wear on the gaskets and polymers throughout the system itself. So you can have some serious issues if they're not miscible fluids. Performance, operating, can become a real headache. Reactivity, not so common with most traditional fluids, but you really want to look in to make sure that you have non-reactive materials put together in these systems, for obvious reasons. But there are specific tests that a fluid supplier will be able to offer, or should be able to offer you, to prove that by mixing one fluid in any ratio with another, you're not going to have any inherent reactivity, or you're not forming something new that's going to be outside of the design specifications of the fluid that you're running. The next issue, contamination. Degradation and maintenance contaminants, they're incompatible with most fluids that you have in there. They're going to immediately degrade the fluid that you have in there, and they could possibly cause issues. Water is another serious thing that you need to look at. If your previous fluid was an aqueous-based fluid, you had a glycol or brine fluid, and switching over to a non-aqueous fluid is a pretty intensive application to undergo. So you're going to want to really work with a supplier on that You need to look at all materials of compatibility, of construction for compatibility, because there's a pretty clear line between what's compatible with aqueous fluids and what's compatible with non-aqueous fluids. What's more common, though, is when someone's changing out a degraded fluid and switching to a new one. So oftentimes use a cleaner or bring somebody in to apply a cleaner in between the refill. Be very cautious of what that cleaner is. If it's an aqueous-based cleaner, don't do it. It's going to cause more headaches than it's worth. If it's a solvent-based cleaner, you need to make sure that that solvent's not going to cause problems to the new fluid when you put it in. And then, of course, there's moisture contaminants that can happen when you leave a system idle for too long as well. So one key point that we want to make here, because it gets brought up often, and this goes back to credibility of claims as well, there's a significant difference between, and it might not be obvious, but it is critical and significant, between compatible and comparable fluids. All right? You need to think beyond just chemical compatibility. For instance, a kind of silly but relevant area you're looking at here might be vodka is compatible with water, but I don't think you need to be mixing them to use as your to put in your bottle when you're running a marathon, right? So just because it's compatible and it'll mix together, it does not mean that it's something that you should go forward with blindly. You need to really think beyond that. One of the first claims that you'll ever see in thermal fluid competitive situations is, yeah, the fluid that you have in there now, our product is compatible with that. Well, it may be compatible chemically, but look deeper. If it's inferior, if it's got quality issues, if it's not the same design, it's not as engineered, it's not as high superiority fluid, it can still create similar failures as if it was incompatible. Long-term performance will certainly be an issue when you're mixing inferior products with a product that has more design to it. And also, if you're upgrading your fluid and you're putting it into a system that has inferior product or degraded product, you might be doing more damage to the new upgraded fluid than you are doing help to the old fluid. So those are considerations that you need to put into place when you're looking at your situation and your selection process. Make sure you consider the entire associated value offering. One supply, and that goes back into the supplier as well. One supplier might have better credibility than another, might have better stocking options. They might have a chemically comparable fluid or compatible fluid, but the service level you're going to get is nowhere near compatible or comparable. The inventory areas, the lead times, take all of those things into consideration. Really evaluate that claim of compatibility versus comparability. Next consideration, and this is always a big one, we're really going to start limiting things down here, and we're transitioning into a situation of considering cost versus your performance. All right, so critical analysis near classification extremes. We talked about those primary classifications way back when in the beginning of the webinar. We said mineral oils, natural organic hydrocarbons have certain extreme maximums, minimums and maximums, and the aromatic or synthetic products allow you to extend that to a higher range. So it becomes critical to really analyze that when you're right at the extremes of those limitations. A safety cushion of an extended temperature range of a synthetic comes at a cost, and that cost is, believe it or not, 3 to 4 times per gallon cost between the high-performance synthetic products and the highly engineered mineral oil products. So you need to make sure that you're really paying for what you really need to get out of this, and that's by going through a total life cost analysis. What's the top-up rate that they recommend? If you're switching to a supplier that requires a 20% a year best practices top-up rate, that's going to come at a cost. Do you really need to do that, or should you just say, I would rather have my fluid analyzed and make my decision on top-up rate or switch-out rate based off of that? Waste removal versus recycling. Synthetic aromatic products typically require you to have a waste removal service, which comes at a cost, versus a general oil recycling service that can come in and just remove the product for you, and depending on the cost of oil, may give you a credit towards that. The rate of replacement. If you're at that extreme operating temperature range, if your fluid that you're looking at is limited to 600, but your process calls for 590, rest assured that you're going to be replacing that fluid more commonly than not. So rate of replacement is something really key to put into. The upfront capital investment, or the upfront investment of putting into the aromatic fluid 3 to 4 times the cost, well, if the life cycle of that is expected to last 5 or 6 times the life of the mineral oil, that's going to be something that you can really consider. Next will be process value-added services that you get with the fluid from the supplier. If you're switching to a product that comes at a lower cost up front, but they're not able to give you the upfront information, not able to lay out what their value-added services are, expertise and reputation-wise, then your total cost at the end of the day will likely be higher. So that's something really important to take into consideration. Next, we're looking at process controls versus fluid controls. And that's in quotations on purpose, because fluid controls are typically very limited. And by that I mean the additive packages that you look at, or a higher flash point fluid. Someone's really concerned about flash point, decides to buy a fluid that advertises a 650-degree flash point, right? So unfortunately, a lot of times those additives or those, that kind of a fluid is going to cause more long-term detriment to your system than one that doesn't. So you're also typically going to pay more for those. So process controls are going to be more important, more effective, and long-term less expensive. And what do we mean by process control? So process control is going to take into consideration you're going to need to make some kind of a modification to your system. Side stream filtration, inert gas blanketing on the expansion tank. So let's take a real quick example of that. You have oxidation concerns, and the last fluid you had gave you a lot of oxidation problems, created sludge. There's a lot of degradation based off of that. So you choose to move forward and find something that offers you the best oxidation protection you can find in your fluid. You'll be much better off by making an equipment modification to put an inert gas blanket on your expansion reservoir. That completely eliminates the potential for oxidation if it's installed and operated correctly, and will be a much less expensive and much more fail-safe decision to make than choosing to go with an oxidation-resistant product moving forward. And that's a cost factor that you need to put up front over the long term. So that's really all comes down to considering the bigger picture. You have equipment costs, you have unplanned maintenance, downtime, and safety. These all need to be taken into account. So, now you're at the point where you've made a decision on what type of heat transfer fluid is going to best suit your process specifications. You evaluated your upper operating temperatures. You've looked at the environmental implications that your plant is able to take on. You've looked at budget to see how much you're willing to spend. You've weighed out your cost versus performance, looked at the total big picture. And now based on that evaluation, you've decided on either A, you've got a natural organic mineral oil-based chemistry that you're going to go with. It's going to give you great stability and performance, but it's going to be limited to temperature, but that's okay. Or B, you need to move to a higher temperature synthetic aromatic-based product. It's going to extend your range and give you higher thermal stability capability, but that's going to come along with trade-offs of greater initial investment and possibly some limitations on storage, shipping, waste removal, environmental issues. You've done that. You've done everything that we've done. You've navigated your way to this point. And now it's time to narrow even further the available options within those remaining candidates. Let's really compare product A with product B, fine-tune the selection to optimize the value that you're going to get. So let's review the most important aspects in competitive benchmarking reviews. So for competitive benchmarking, final product compositions vary significantly depending on the intended outcome. So true thermal fluid manufacturers, true experts in this field, have the ability to engineer fluids to balance the primary factors, such as their stock ratios that they use, to give you an ideal ratio of physical properties, density, viscosity, etc. The level of process refinement Is the product hydrogenated? Is there hydrotreating? It's a purity consideration. And is this the ability to add formulation of additive packages? And that's really a design functionality consideration. So the key competitive differentiation factors that are product-based, we talked about before: heat transfer efficiency, high purity, and thermal stability. And those are what's going to give you a well-designed heat transfer fluid. So purification, we spoke about before at length. Level of thermal fluid purification goes beyond toxicity considerations. You need to remove the impurities that catalyze fluid degradation and foul equipment surfaces when continuously exposed to high operating temperatures. And those benefits go, like we said, go beyond just toxicity. The extended service life of the fluid, reduction in maintenance activities, lower risk of equipment failure, and greater consistency in performance. The next key point was heat transfer efficiency. Now, these are things that you need to take in comparison with one fluid to another. Keep in mind, that's what we mean by benchmarking. You're looking at two different fluids. Heat transfer efficiency is where you can take the data sheet of product A and the data sheet of product B, put them together and say, what's going to give me the best heat transfer efficiency? Well, how do you do that? Well, heat transfer efficiency is really used to represent we use the inside film coefficient, this H sub I designation, to represent heat transfer efficiency at any given set of operations. So you know that. We already talked about conditions of the system. You know those things. You can apply the data of each fluid at those specific operating conditions and determine by the data which fluid is going to offer you better heat transfer efficiency. Okay, so fluid with a higher heat transfer efficiency is going to be considered to be superior and give you better performance over the long run. Higher the inside film coefficient, the more efficient the fluid is. And these are calculated based on thermophysical properties, and we'll go through which the important ones are, and process-specific flow dynamics, like the pipe size, fluid velocity, temperatures, etc. So efficiency is determined by an ideal combination of low viscosity, high density, high thermal conductivity, and high specific heat capacity. Okay, so those advantages, weighed out and ratioed out and designed, will give you better heat transfer efficiency at any proposed operating temperatures and flow conditions. How do you determine those things? Well, your thermal fluid supplier will have that on the data sheet. If they don't, then request it if it's not published. If they aren't able to give it to you at an extended temperature range, dismiss them as a thermal fluid supply option because you should be able to get at least those characteristics. The quality manufacturers take great care in engineering fluid that balance those characteristics. The next key criteria, thermal stability. And this is done in the lab. This is a tested simulation of what happens inside your heater pipes or at the surface of your heated surface. It's something that happens over 500 hours. It's done at a temperature which is going to really push the limits of the fluid. And it really is a snapshot of how well a fluid will resist damage due to the thermal energy that's being applied to it in your system. It's how much longer is a fluid going to last than another is something you can take away from that. How much fouling and how much degradation can you expect due to thermal breakdown? A fluid with higher stability will cause less of that. So really when you're looking at this, greater thermal stability fluids will result in higher heat transfer efficiency over time, longer fluid life, and lower potential for system damage, safety hazards when proper operating conditions are followed. Request a thermal stability analysis between two fluids that you're considering. That'll really give you a great idea on what fluid may be better than the next, or what fluid chemistry in general might be better than the next. Additional considerations, thermal expansion, oxidation resistance, fouling resistance, and vapor pressure are also key benchmarks. Now, another key point, credibility. Credibility comes in the form of multiple things here. Your thermal fluid supplier's credibility and the claims that that supplier is making. You always need to make sure you're insisting on excellence from your supplier, okay? Strategically stocked products, one key point. Where is the supplier keeping the products? 24-hour emergency shipping available? That might not be something that's important to you if you're not running continuously until you actually need the product when it's after hours. local technical and commercial support. Full-time sales support, 24 hours a day. Do they offer this? Is there fluid support, nature around just the fluid itself, or the equipment and the process-specific expertise? Talk to your equipment manufacturer. See who they recommend, not just based on the fluid, but the expertise they have. Do they have compliance and technical resources? Is there an access to a network of research and testing? Do you have testing facilities? Why is technical support so important? Well, fluid degradation is going to be there no matter what. And you need a supplier partner to be able to minimize the rate at which that degradation happens. So finding somebody that's able to offer you that up front and be there with you through the entire life cycle is going to be key. Do they offer a fluid analysis program? That's the most reliable tool for keeping your system running without problems. So make sure that your supplier offers this, and see if they actually offer this in their own facility or they're doing it through third parties. That's key based on turnaround time, expertise. Are they giving you a lube oil analysis, or are they giving you something that's really specific to your operation and your fluid? You should be able to ask that up front and have them prove that credibility to you. And credibility of claims is really important as well. Want to make sure if someone's claiming something based on their fluid, it's very oxidation resistant or it's got these additives, tell them to put that in the scope of what's really important for your system itself. Make sure you're always comparing apples to apples when you're looking at credibility claims. And go to both sides and say, this guy's saying this one's saying this, prove to me why what you're saying is more important and more credible. So at the end of the day, all of this is here to avoid the rough waters. Protecting your people, protecting your equipment investment, running an efficient operation, and avoiding production downtime. Using the wrong fluid will lead to accelerated degradation, failures, surface fouling, increased maintenance, and decreased efficiency. This is why it's so critical. Operating outside of design specifications and failing to adhere to basic preventive maintenance practices will lead to irreversible damage of the fluid and the equipment. Primary concern here is the safety of your people. When run properly with the correct fluid, and that's a key point, heat transfer fluid systems are safe and low maintenance. The inherent dangers of a high temperature operation increase exponentially when these factors are taken for granted. Choosing a reputable specialty supplier, they can work with you to select a high quality engineered heat transfer fluid and co-develop an operation-specific preventive maintenance plan. That's going to give you a much higher return on your upfront investment, prolong your fluid life, minimize your downtime, and this critical element of your operation will run with increased safety, efficiency, and reliability without a high demand on your personnel. With that, thank you very much for your time.